Hi, this is Schwartz from MasterMathMentor.com. This is video BC13. The topic is vector valued functions and it covers the BC manual pages 68 through 70. In the previous video, we studied vectors. These were constants. Each vector was one magnitude, one direction. But vector forces change. Just the act of shoveling snow or planting vegetables requires variable forces in various directions. Earlier, we defined a plane curve as the set of points f of t, g of t, satisfying the parametric equations x equals f of t and y is equal to g of t, where f and g are continuous functions of t on some interval. We now define a new type of function called a vector-valued function of the form r of t is equal to f of t I plus g of t j. A vector-valued function, sometimes called a vector function, takes the variable t and returns a vector. The domain of a vector-valued function is the set of all t for which both component functions are defined. In problem 1, you are given three vector-valued functions, and you are to find the domain of each function. In A, we know that the square root of t plus 1 has to be non-negative, so t must be greater than or equal to negative 1. We also know that 4 minus t must be positive, so that means t is less than 4. So the domain of this vector-valued function is t greater than or equal to negative 1, less than 4. In B, we have e to the negative ti, and t can be any number we want. But the inverse sign is only defined on negative 1 to 1, and therefore t must be a value between negative 1 and 1. In C, we know that because of the I over t, t cannot be 0. Since secant t can be written as 1 over cosine t, we know that t cannot be any values where its cosine is equal to 0. And that will be any expression in the form of 2n plus 1 pi over 2, where n is an integer. Shown is the vector-valued function r of t equals t minus 5I plus j. And various values of t are shown in the sketch. The graph is a set of infinite number of vectors. This might represent a fan that oscillates. At t equals 0, the fan gives a force of wind with a magnitude of the square root of negative 5 squared plus 1 squared, which is the square root of 26. At t is equal to 1, the fan gives a force of wind of magnitude the square root of negative 4 squared plus 1 squared, which is equal to the square root of 17, and so on. At t equals 5, the force is 1. After t equals 5, the force gets greater. In vector-valued functions, we are usually interested in the path of the endpoints of the vector. And since the vector has a constant for the j part of it, the path would be the line y is equal to 1. Let's examine the vector-valued function r of t equals 4 cosine t I minus 2 sine t j, t running from 0 to 2 pi. To get a sense of this, we will change the vector-valued function first into a parametric and then into a rectangular equation so we can see its path. So x equals 4 cosine t and y equals negative 2 sine t. Squaring both, we get x squared equals 16 cosine squared t and y squared equals 4 sine squared t. That gives cosine squared t equals x squared over 16. Sine squared t equals y squared over 4, and since sine squared plus cosine squared is equal to 1, we get x squared over 16 plus y squared over 4 is equal to 1. We graph this expression and find that it graphs an ellipse. Remember, though, that this is the path of the endpoints of the vectors. I show three vectors at t equals 0, t equals pi over 6, and t equals pi over 2. An object that has these forces applied to it will travel along this path. For instance, if someone were caught in a whirlpool that is represented by this vector function, he would move along the elliptical path and theoretically never get out of the whirlpool. Let's review. A rectangular equation, or a function, describes a path. It is usually expressed, if possible, y is equal to f of x. Parametric equations describe a path over time. These are expressed as x is equal to f of t, y is equal to g of t. A vector valued function is a set of vectors over time. It is in the form of f of t I plus g of t j. These are all different types of expressions, but their paths can be the same. So in the example, y equals x to the third minus 2x squared plus 3x minus 1, which is a rectangular equation and a function, we can express this parametrically as x is equal to t and y is equal to t cubed minus 2t squared plus 3t minus 1. The vector valued equation would be ti plus t cubed minus 2t squared plus 3t minus 1 j. Again, all three are different, but the paths that they create are exactly the same. Page 69 has a set of rules in working with vector-valued functions: adding, scalar multiplication, vector multiplication, limits, continuity, and derivatives. Rather than go over this set of rules, we will look at specific problems and then refer to the rules, which all make perfect sense. In number 5, we're given that r1 of t is the vector-valued function t squared I minus 4t minus 1 j. r2 of t is the vector-valued function 2t squared plus 3 I plus 2tj. And h of t is the function 1 over t. There are 6 expressions that we need to simplify. A reads r1 of t minus r2 of t. We've done this type of problem before. We simply subtract the I components and the j components. So we get negative t squared minus 3 I plus 1 minus 6t j. B asks for the magnitude of the vector we just found. So we square each component and take the square root of it. So we get the square root of negative t squared minus 3 quantity squared plus 1 minus 6t quantity squared. Simplifying, we get t to the fourth plus 42t squared minus 12t plus 10. C asks for the magnitude of r1 of t divided by the magnitude of r1 of t. There is no calculation to do here. This is the definition of a unit vector whose answer is 1. You may want to go through the work and show that the answer is 1. D asks for r1 of t dot r2 of t. This is a dot product. And remember, a dot product is a scalar. So we multiply the I components and also the j components and take their sum. So our answer is t squared times 2t squared plus 3 minus 4t minus 1 quantity times 2t. Expanding that expression, we get 2t to the fourth plus 3t squared minus 8t squared plus 2t. Final answer, 2t to the fourth minus 5t squared plus 2t. Our answer is not a vector, our answer is a scalar. E asks for h of t times r1 of t. H of t is a function, and we are multiplying that by a vector, so we multiply the h of t by each term in the vector, getting ti minus 4 minus 1 over t j. F asks for h of t times r2 of t squared. R2 of t squared is a dot product, R2 of t times R2 of t, which is a scalar. And h of t is a scalar, so this is a scalar times a scalar, which is a scalar. R2 of t is the dot product, and we get 2t squared plus 3 quantity squared plus 2t quantity squared. Expanding that, we get 4t to the fourth plus 12t squared plus 9 plus 4t squared. And multiplying that expression by 1 over t, we get 4t to the third plus 16t plus 9 over t. In 6, you're asked to take the limits of the vector-valued function. To do so, you take the limit of each piece. And if the limit does not exist for one piece, then the limit does not exist for the entire problem. In 6a, we're asked to find the limit as t approaches 3 of ti plus t squared minus 9 over t minus 3j. The first part is 3i. The second part can be done either by plugging in and then factor cancel, or by using L'Hopital's rule, and we get 6j. Final answer, 3i plus 6j. B asks for the limit as t approaches 0 of e to the negative ti minus sine t over 2tj. We plug in for the I, and we simply get e to the 0 I, which is simply I. The second part is 0 over 0, so we can use L'Hopital's rule, getting cosine t over 2, and plugging in 0, we get negative 1/2 j. Answer, I minus 1/2 j. Part C, the limit as t approaches infinity of e to the negative ti plus 5t plus 1 over t j. When we write e to the negative t, we can write that as 1 over e to the t, and the limit as t approaches infinity is 0. So the i's part is simply 0. The second part is the highest power coefficient over the highest power coefficient, and we get 5j as an answer. Number 7 asks where the vector-valued functions are either continuous or not continuous, if it's easier to state it that way. We simply look at the continuity of each piece and put them together. If either piece is discontinuous at all values of t, then the vector-valued function is discontinuous at all values of t. 7a is r of t equals 1 over ti minus tj. 1 over t is discontinuous at t equals 0, and t is continuous everywhere, so this vector-valued function is continuous at negative infinity 0 union 0 to infinity. B, r of t equals the natural log of t minus 1i plus tangent tj. The natural log is continuous when the expression is greater than 0. So t minus 1 is greater than 0, meaning t must be greater than 1. And tangent is continuous at all values, pi over 2, 3 pi over 2, etc. So continuity here is that t must be greater than 1, but not equal to pi over 2, 3 pi over 2, etc. C, r of ti is equal to cosine ti plus inverse cosine of tj. Cosine t is continuous everywhere, but the inverse cosine is only continuous and defined between t equals -1 and 1. So that is your answer. Finally, we get to work with derivatives and integrals of vector-valued functions. So if we have u and v as differentiable vector-valued functions of t, and h of t is a differentiable real-valued function of t, while k is a scalar, then the following properties are true. First, addition and subtraction. The derivative of u of t plus or minus v of t is, as expected, u prime of t plus or minus v prime of t. Scalar multiplication. The derivative with respect to t of k u of t allows us to take the k to the outside and express this as k u prime of t. Function multiplication. We want to take the derivative of h of t times u of t. Remember that h of t is a real-valued function while u of t is a vector. But the product rule still holds. We look at h of t times u prime of t plus u of t times h prime of t. Our answer will be a vector. The one we see a lot is the vector product rule. The derivative with respect to t of u of t v of t is by the product rule u of t v prime of t plus v of t u prime of t. However, since u of t times v of t is a vector times a vector, which is a scalar, it sometimes is easier to do the dot product first and then take the derivative of your answer. We will show that in our examples. Finally, our integration rules. Suppose that r of t is a vector-valued function f of ti plus g of t j, where f and g are continuous on some interval ab. The integral of r of t will be the integral of each piece. The integral of f of t dt I plus the integral of g of t dt j. When we integrate, though, we must remember that we have constants. So we will have a c1i plus a c2j. So the answer is best expressed as the integral of f of t dt plus c1i plus the integral of g of t dt plus c2j. If we are taking a definite integral between a and b, we simply integrate each piece from a to b. So our answer is the integral from a to b of f of t dt I plus the integral from a to b of g of t dt j. In number 8, we're given that the function f of t equals t squared plus t. The vector u of t is equal to 1 over ti minus j. And the vector v of t is equal to t squared I minus natural log of t j. We are asked to find the derivative of two products. We will work them two ways. The first, we will apply the product rule. Secondly, we will multiply first and then take the derivative. In A, we will apply the product rule first. So we have t squared plus t times the derivative of the vector u, which is -1 over t squared I, plus the vector 1 over ti minus j times the derivative of the function, which is 2t plus 1. We multiply out, and we get -t minus 1 over ti plus 2t plus 1 over ti minus the quantity 2t plus 1j. Putting the i's together, we get simply a plain old I minus quantity 2t plus 1j. The alternative is to multiply the function times the vector first. So we will be taking the derivative with respect to t of t squared plus 1 times 1 over ti minus j, which turns out to be t squared t plus 1I minus quantity t squared plus tj. Now the derivative is easy. We simply get I minus quantity 2t plus 1j. In this problem, because the multiplication was simple, multiplication first was better than applying the product rule. We now want to take the derivative with respect to t of u of t, v of t. There are two ways to handle this. Again, we will deal with the product rule first. So we have u of t, which is 1 over ti minus j, times the derivative of v of t, which is 2ti minus 1 over tj, plus v of t, which is t squared I minus natural log of tj, times the derivative of u of t, which is negative 1 over t squared I. We now multiply out as we have vector times a vector plus a vector times a vector. Using the dot product rule, we get 2 plus 1 over t minus 1, and that becomes 1 plus 1 over t. The second option is to multiply first. Since this is a dot product, we multiply the components of u plus the components of v, and we simply get t plus the natural log of t, and now the derivative of that is simply 1 plus 1 over t. It should be clear that multiplication first is generally easier because we only have to do one dot product as opposed to two. In number 9, we are taking integrals and definite integrals of vector-valued functions. We simply take the integral of each piece, remembering that we do have a constant of integration, which will end up being a vector. In 9a, we have the integral of t squared I plus the natural log of tj. The integral of t squared is simply t cubed over 3, but to take the integral of the natural log, we use integration by parts, where u is the natural log of t, du is 1 over t dt, dv is dt, and v is t. And we end up getting t, natural log of t, minus the integral of t times 1 over t, which is simply 1. So this integral turns out to be t, natural log of t, minus t, j, plus c. Realize that in reality, c is a constant vector. It is really c1i plus c2j. It is understood when we use vector-valued functions that when we write c, we are talking about a constant vector. In b, we are asked the integral from 0 to 1 of e to the negative ti plus 1 over t plus 3j dt. Integrating each piece, we get negative e to the negative ti plus the natural log of the absolute value of t plus 3j evaluated from 0 to 1. So plugging in the 1, we get negative 1 over ei plus the natural log of 4j. And now plugging in the 0, we get minus quantity negative I plus natural log of 3j. Putting the i's and j's together, we get 1 minus 1 over ei plus the natural log of 4/3, which can be written as the natural log of 4 minus the natural log of 3j. In C, we'd like to find r of t, which is the integral of the sine of 2ti plus 1 over t squared plus 1j dt, given the fact that r of 0 is equal to 1/2 I plus j. First, when we integrate, we get r of t is equal to negative 1/2 cosine of 2ti plus the inverse tangent of tj plus c. Plugging in 0, we get negative 1/2 I plus 0j plus c, which we know is equal to 1/2 I plus j. And that makes c equal to I plus j. When we write our final answer for r of t, we don't add on the plus c, we add on each component of c. So r of t will be 1 minus 1/2 cosine of 2ti plus 1 plus inverse tangent of tj. The reason that we learn all these rules for derivatives and integrals of vector values functions is to study motion on curved paths as opposed to motion on straight line paths, which we studied in AB calculus. The next video will work exclusively on motion on curved paths.